Hello everyone. Thanks for viewing this Supercomputing Conference 2020 presentation talk. In this talk, I'm going to introduce CallFlow, a tool to visualize hierarchical performance profiles of parallel codes, and also explain how we enable scalable comparative analysis on an ensemble of such profiles. This is a collaborative effort from visualization researchers from University of California, Davis, and high-performance computing experts from Lawrence Livermore National Laboratory and University of Maryland, College Park. Large-scale computational resources like Sierra enable scientists to explore complex scientific phenomena and advance the frontiers of human understanding in multiple areas such as astronomy and climate change. In order to maximize the amount of science per dollar, computational scientists and HPC experts continuously strive towards optimizing the performance of their simulation codes. To do this, computational experts continuously ask themselves, is their application performing as good as it can? To answer this question, performance analysis is usually performed to identify and eliminate bottlenecks. Typically, large-scale scientific applications demand a lot of optimization effort to understand how different application parameters affect the performance. Diagnosing the true cause of performance bottlenecks typically requires a simultaneous understanding of the code execution, which usually comprises of multiple libraries, and the runtime performance from multiple parallel processes. In particular, performance analysis commonly comprises of four analysis tasks. To detect performance issues, it is crucial to pinpoint call sites that consume most execution runtime. To ensure consistent workload distribution across processes, we need to identify call sites with high load imbalance. To determine which optimization is better, we would require to compare the performance across executions. Finally, to understand the effects of various optimization techniques, we need to study the performance variability across multiple executions. Key indicators of performance analysis are usually captured through performance profiles. Sample performance profiles are collected by forcing an interrupt at every nth instruction. In general, they record two kinds of information: exclusive metric and inclusive metric. Inclusive metric represents the time consumed by a call site along with its children call sites. Say for example, in this example, we have foo1 calling bar1 and bar2. So the inclusive runtime is added up for foo1 and it becomes 6. The collected call sites can then be aggregated by their call paths to form a tree structure popularly known as calling context trees or CCTs. CCTs can further be aggregated by merging their call sites with the same function name called call graphs. A majority of existing tools generate CCTs for the whole application, like HPC Toolkit. These include the call sites of the libraries it depends on. However, typically, only a small fraction of these nodes in a CCT are of interest. But such nodes are usually buried deep in the tree, and identifying them could be challenging. For example, HPC Toolkit uses an expandable tree visualization, requiring users to toggle and expand multiple hierarchies from top-down and bottom-up call stack. However, expandable tree layouts do not scale well with the size and depth of CCTs. Also, the user would lose context during analysis. On the other hand, several tools have combined traditional node link layouts and visual encoding techniques to direct the user towards the performance of calling contexts. However, visualizations using node link layouts become intractable as well. This is especially true for large-scale applications containing hundreds to thousands of call sites. Recently introduced performance analysis tool Hatchet provides a programmable interface to perform performance analysis on a variety of formats such as HPC Toolkit, Caliper, gprof, cprof, and so on. They enable analysis by converting hierarchical performance data into a pandas data frame and associate the call sites in the call graphs to their performance. Although Hatchet provides basic visualization techniques to visualize the data, these visualizations are mostly static and do not support interactive analysis. For example, on the left is shown a Lulesh simulation on 512 cores. The average exclusive runtime is color mapped on the text, and we can immediately find out the most expensive call site, calc glass for elements. However, the interface requires the user to programmatically change each time before performing the visual analysis. Additionally, their analysis is also limited to a single execution. Similar to other node link layouts, this tree-based visualization approach would still suffer for executions that contain a large number of call sites. CallFlow, on the other hand, extends the interface of Hatchet to provide an interactive exploration of profiles. CallFlow enables ways to encode information based on both inclusive and exclusive metrics. This helps to find the most important call sites easily. To help associate the performance of per process information, CallFlow also provides additional views such as histogram, scatter plots, and box plot views that help to associate data much easily. We further aggregate the contextual information using the available semantic information to what we call supergraphs. In this example, the call graphs are grouped by the module or library they belong to. This helps us immediately spot the most expensive call sites inside a library. Our interface also extends the analysis to multiple profiles in the same time. Studying large number of profiles is critical as large-scale applications require significant optimization efforts to understand how different application parameters may affect the performance. In this process, experts conduct a variety of test runs by varying multiple configurations to identify optimal execution parameters and configuration. To support this, CallFlow enables the user to modify the profile they want to view. Although CallFlow supports studying individual call graphs, comparison of two or more call graphs requires the user to analyze them individually. Comparison of multiple call graphs is essential to identify the overall trends across the performance metrics in an ensemble. So to improve this, in this work, we improve CallFlow's functionality to introduce two new analytic modes. Ensemble mode, which visualizes the performance variation across multiple call graphs, and a diff mode, which directly compares two call graphs and a selected call graph against the ensemble. In the remainder of this talk, I will first cover how we construct the supergraph and then discuss the multiple profile scenario where we construct an ensemble supergraph. Like I mentioned earlier, the scale and complexity of CCTs and call graphs poses significant challenges for interactive visual exploration. CallFlow supergraphs, on the other hand, utilize the contextual information from the code to provide a high-level overview. This is particularly useful in the case of modern software abstractions that have numerous intermediate call sites which are not relevant to performance analysis. For example, library 4 is being called from different code modules, library 1, library 2, and library 3. These repetitive calls from different code modules form similar subtrees with different parent nodes. To reduce these repetitive calls, we first filter out these call sites by providing a user-provided threshold and aggregate the CCT to a supergraph based on the available contextual information. These supergraphs can interactively be modified and studied using the splitting operations to further reveal the callers and callees for further analysis. To encode this supergraph, we use a Sankey diagram. The Sankey diagram provides a high-level overview for the code execution. The nodes can be colored based on module or inclusive or exclusive runtime based on user's choice. The height of the node corresponds to the inclusive metric, whereas the edge flow corresponds to the control flow of the execution. To highlight the nodes of interest, users can modify the runtime range and CallFlow will update the encoding on the supergraph. The interface supports various interactions such as zooming, panning, for exploring large supergraphs. Hovering over a node reveals detailed information of the call sites inside a particular supernode and their properties. Further, each node in the supergraph is embedded with a mini histogram that shows the process distribution. This histogram allows the user to spot load imbalances among processes across different supernodes. To create the ensemble supergraph, first we perform a unify operation on individual CCTs to construct an ensemble CCT. Unify operation merges all the calling contexts that share the same caller-callee relationships across the CCTs. A call site from CCT is considered equivalent to the call site from another CCT if they have the same calling context across the two runs. The corresponding metrics are aggregated and stored as individual vectors. The unification enforces graph equivalence by assigning a null value to the missing nodes in any CCT. For example, the bar call site is actually missing in the second and the third CCT, so they have been assigned a value of null. Next, the ensemble CCT is converted to an ensemble call graph by merging the call sites with the same function name. For example, the bar call site occurs in multiple calling contexts which are further aggregated in a call graph. The associated vectors are element-wise added to summarize the performance runtime on each call site. Finally, the ensemble call graph is aggregated to a module-level ensemble supergraph through user-defined filtering and grouping operations similar to a single supergraph. To encode the performance variability, we encode each supernode using ensemble gradients. This corresponds to the distribution of inclusive or exclusive metric by user's choice mapped vertically along the height of the node using a white to red color map. The colors are mapped consistently across all nodes to allow evaluation of distribution not just within a single node but across supernodes as well. Such an encoding preserves the notion of resource flow from one module in the call graph to the other across executions. For example, the distribution of the MPI module is spread across multiple bins. On the other hand, the execution runtimes for the calc-Lagrange module is actually along the extremes, making a clear distinction of performance variability. Additional runtime information can be revealed by toggling the text guides by clicking on the supernodes. These text guides mark the bins of the histogram and also display the minimum and maximum runtimes of the execution among the ensemble. During analysis, the user might find two executions that exhibit a variation in the ensemble distribution. To facilitate a further comparative analysis, we compute a diff supergraph that subtracts the mean runtime across the supernodes between the call graphs. The resulting diff view is visualized using a Sankey diagram and is colored using a green-red color map, where the hues of red color highlight the performance slowdown and the hues of green color highlight the performance speedup. CallFlow additionally provides two supporting views that enable performance correlation analysis. The histogram view provides an enlarged view of the mini histogram along with the shadow lines. The shadow lines indicate the rank to bin mapping to assist the user explore the connection between slowdowns in the MPI ranks and the physical domain. Although shadow lines can create visual clutter, especially for large processor counts, it is a desired visualization since it indicates the code behaves normally. More crisscrossings indicate efficient mapping to the hardware domain, while a less visual clutter denotes that certain runtimes are not well correlated to the rank IDs. This implies a load balance as shown in the bottom figure. The scatter plots help reveal the correlation between the inclusive and exclusive runtime metrics. If there is a correlation, then we expect the processing elements to form clusters as shown in the bottom image. Next, To enable performance correlation across ensembles of supergraphs, we show histograms and scatterplots of a selected supernode in three modes. Call site mode shows the distribution of runtime metric with respect to individual call site. Call graph mode shows the distribution with respect to the call graphs. Finally, the MPI rank mode shows the distribution across the rank IDs. These three modes enable the user to compare the runtime performance of a selected run across the ensemble. CallFlow supports two graph splitting operations, split node by entry call site and split node by parent. Both operations allow the user to prune a high-level overview and reveal low-level call sites that consume most resources. To split by entry functions, we show the list of call sites on a site panel from which the user chooses multiple functions to reveal. Once chosen, the graph view is updated to include the selected functions in real time. Splitting by parent, on the other hand, reveals the caller's call sites of a selected node from the hierarchy. In this example, we show the two entry functions of the Leos module and also reveal its parent functions. The histogram can further be used to enable side-by-side comparative analysis to compare the runtime among processes by allowing the users to click and drag on the histogram using a brush. This splits the graph view into two halves, revealing two supergraphs for the selected and non-selected bins respectively. Finally, we show CallFlow's usefulness on a real-world application, Lulesh by studying for load balancing across multiple processes. Lulesh is a proxy application used for modeling large-scale hydrodynamic simulation. For this study, we compare the performance of two execution configurations. First experiment is a traditional MPI run, where a single MPI rank is placed on every process. The second experiment runs Lulesh with over-decomposition, where multiple MPI ranks are placed on every process. In general, over-decomposition enables communication among processes and improves the performance. Comparing the heights on the supernodes, we realize that the application performance improved with over-decomposition at an average of 44%. Next, comparing the histograms, we notice that the per-process distributions of the supernodes are skewed, conveying the load imbalance exists due to inefficiency in the communication. These two inferences would have been difficult to deduce with traditional CCT visualizations, since modules like libPSM and AMPI would contain hundreds of call sites. We further investigate this phenomena by clicking on the Lully supernode to reveal the corresponding histogram view. We can immediately spot the few processes that are overworking with 170 seconds as shown on the right side of the histogram. The performance of heavy MPI ranks can then clearly be distinguished using the side-by-side overview by performing the brush interaction, which splits the call graphs into two. As a next experiment, we study the weak scaling of Lulesh across 8 execution parameters by varying the number of processor counts. The aim of the experiment was to identify call sites that exhibit inconsistent or unexpected runtime behavior. Although the ensemble gradients across supernodes exhibit good weak scaling, as they have very little variance in runtime, the text guides reveal two cases of out-of-order runtimes, especially for the MPI module and the CalcForce module. This can be seen through the text guides, as we can notice the 27 core runs is followed by a 216 core runs and then followed by 64 and 125. This implies that the 216 core run is much faster than 64 and 127 cores runs, which seems like an anomaly. To further surprise, we also notice the same pattern existed in all the nodes of the CalcForce module by performing the split graph operation. Next, we further investigate this phenomena by comparing the 64 cores with the 27 cores, and also comparing the 216 cores with 125 cores. As we notice, the diff view clearly distinguishes the performance variability exhibited by the CalcForce module. There is a clear performance slowdown in case of the 64 case, and there is a performance speedup in case of the 216 core case. The diff view clearly distinguishes not only the performance degradation, but also the degree to which the performance has degraded. In comparison to the CalFlow module, the other modules, like for example the leapfrog or the timer module or the relation module, show little performance variation. To summarize, CallFlow helps users identify performance bottlenecks in their parallel codes effectively, leading to potential optimizations and improved overall throughput of applications. Catering specifically to the target audience, CallFlow customizes and enhances the understanding of call graphs using a module level representation called supergraph, and also uses multiple linked views to provide holistic exploration of CCTs. Through a set of interactions on the underlying supergraph, CallFlow provides a high-level overview of the CCTs and also provides the ability to drill down for detailed information. CallFlow also supports visual mediums that enable comparative analysis on two or more call graphs. Additionally, CallFlow also supports a comprehensive list of profile formats like HPC Toolkit, Caliper, and cProfile. To reach a wider audience, CallFlow is now publicly released under the MIT license and is available on GitHub. Please feel free to clone the project and check it out. Thank you.